Attendees are in listen-only mode.
Nobody's supposed to start it.
Oh, it just started?
Yeah, I just try to share my screen. Can you see my screen now?
No.
Yeah, I can see your Google. Yeah.
Should be. It's coming, right?
Yes. Maybe in the presentation mode, probably. Yeah.
Yeah. 1 second. It's a little bit slow here. So it should be in full screen, right?
I think so. Yeah.
So when I share my screen, I cannot see myself. Is that correct? I don't see any, videos anymore.
Only you should be. Yeah. I can see myself, and I don't know.
Right. That's okay.
Yeah. Okay. So. Someone started the broadcast and it was not supposed to be started.
Okay.
So I'm trying to stop it, but I don't know how.
Recording and
yeah,
no.
Someone started it. I don't. Hello all and welcome to the UFS webinar. This webinar is hosted by the NWS-OSTI. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS, in both research and operational settings. I am Stacy McKell, and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. So if you have any recommendations for speakers that you would like to present at this webinar, you can email your recommendations to ufs.modeling@noaa.gov. Again, that's ufs.modeling@noaa.gov. Here are a few housekeeping items that I'd like to bring to your attention. Right now, you'll be in listen-only mode due to the high number of attendees, and you will not be able to unmute. If you have any questions now or during the event, please submit them via the Google document that will be provided in the chat box. Presentations last for about 45 minutes, followed by Q&A for 15 minutes. Just type your questions in the Google document during the presentation. Okay, today's presentation will be Model Diagnostics Task Force, a walkthrough of technical vision and diagnostics package. I wanted to quickly show you how to sign up for the webinar notifications and how to view archived information. To the UFS webinar webpage. You go to the portal at ufscommunity.org. You scroll to the event section, you'll see the webinar listed on the page. Okay. So all of these webinars are recorded and made available on the UFS portal. Today's speakers, Aparna, Radhakrishnan, and co-author Wenhao Dong will be introduced by Krishna Kumar. Krishna, I will turn it over to you.
Thanks, Stacy. I would like to introduce two speakers, Aparna Radhakrishnan, who's the Data and Analytics Lead at the Cooperative Institute for Modeling the Earth System, SIMS, at Princeton. And Radhakrishnan is also affiliated with Geophysical Fluid Dynamics Laboratory since 2009, and is presently the technical lead for Model Diagnostics Task Force. Aparna's research interests are to identify and promote usable techniques for climate data access and analysis for a diverse group of users. And I also would like to introduce Dr. Wenhao Dong, who is a postdoctoral research associate at the GFDL and the CPAS program at University Corporation for Atmospheric Research, UCAR, working with Doctors E. Ming and John Crasting. He earned his PhD from Tsinghua University in 2018. And he has broad interest in model diagnostic and environmental data analysis. He's also fascinated by different extreme precipitating systems on various spatio-temporal scales, including low pressure systems, tropical cyclones, mesoscale convective systems, etc. So I would like to welcome first Aparna, who will be speaking about, half time, and then Dong will take over. Thank you. Aparna, take it away.
Great. Thank you so much, Krishna, for that introduction. My name is Aparna Radhakrishnan, one more time, affiliated with Princeton University and GFDL. Happy to be talking here along with Wenhao on Model Diagnostics Task Force. Next slide, please. Yeah, first things first, I would like to acknowledge the entire Model Diagnostics Task Force, especially the framework team. We have other contributors also for the project, so thanks to each one of you. Also, want to thank the funding acknowledgement funders here, NOAA MAP program, and the different cloud awards that we received through CDI and OAR RD HPCS. Next slide, please. So this is going to be a two-part webinar, like Krishna mentioned. The first part is mostly going to be me giving you a background on process-oriented diagnostics and MDTF, mostly covering the technical aspects. The second part is going to be a deep dive on a specific process-oriented diagnostics, MJO in this case, and that will be led by Wenhao. Next slide, please. So you can see how overwhelming this slide is, and I think that is the current state itself. Literature shows, especially IPCC, shows that there are lots of processes and specific phenomena still challenging, still uncertain. So we really need some details. On your right, what you see is the mid-latitude winter precipitation, which is highly dependent on the tropical, extratropical cyclones per the study conducted by Jimmy Booth. So this means if the mid-latitude precipitation in GCMs need to be useful, then it should probably capture the extratropical cyclones in a better way. This is not as simple as it sounds. It means studying different processes like precipitation and latent heat in the cyclonic area and see how the dynamics of the cyclone or the intensity actually changes and what kind of feedback it actually propagates. So this really tells us that the devil is probably in the details and that the representation of several processes and their feedback are of utmost importance for us to identify what the gaps are in understanding a specific climate phenomena as well. Next slide, please. Next slide, you see some of my favorite definitions or excerpts from other AGU presentations telling processes are more about the derivative of the model state with respect to, what things change with respect to what, with respect to time as well. Like Eric Maloney published in 2019 based on an MDTF paper, increasingly models are being analyzed in more detail against observations of specific processes, and that's kind of the spirit in which MDTF is approaching pods. There are many other examples of process-oriented diagnostics, such as this from your right side by Wing et al., developing a process-oriented diagnostics, again centered around cyclones, just in this case as an example. Next slide, please. So there is another side for the coin in terms of challenges, not just the scientific ones, but the things that I want you to glean from this slide is that there's data everywhere. And this data is of varying dimensions, different model output formats, and different other things, you name it. And the users of the data are also everywhere. And ultimately, we want to even diversify the number of users of this data sets. When you think about the domain experts, they are also dispersed everywhere. And with this overwhelming state, we almost always need our results like now. This really calls for collaboration, and without collaboration, this is probably not going to happen, like having the results like now. Next slide, please. So now, what is Model Diagnostics Task Force? I laid a foundation on process-oriented diagnostics. I also told you about the importance of community and collaborations. So Model Diagnostics Task Force, it helps us engage research community developing process-oriented diagnostics. I will be referring to that as pods throughout, to improve the performance of Earth system models at NOAA, NCAR, and DOE. In terms of collaboration, this is a multi-institutional effort funded through the MAP program at NOAA's CPO. History for sure dates back to 2012 when the CLIVAR MJO task force was established. MDTF phase 1 though started in 2015. That's when the public release of the framework was actually made. And there were about 8 process-oriented diagnostics from the first phase. Phase 2 and 3 continuing to be led, or the framework development aspects are continuing to be led by GFDL, with the lead PI being David Neelan, who's also here with us today. So phase 2 and 3, we are going to focus more on collaborations, more contributed diagnostics, and more toward open source software model. Next slide, please. So this is just a glimpse of what the expanded suite of diagnostics are. Some of these are already incorporated into the framework, and some of these are yet to come in. And there are a few others that we haven't captured in the slide because we just got a notice that there are many more diagnostics joining the MDTF in phase 3. But this is to show you that it's spanning across different modeling components, not just atmosphere. We'll be also looking at ocean in detail in phase 3. Next slide, please. So I've been mentioning the word framework a number of times, but I didn't tell you what the framework was. So from phase 2, let me just throw you this definition or explanation here. MDTF Diagnostics Framework. So developing process-oriented diagnostics is a challenge, but the other challenge, if you want more collaborations from other institutions as well, is to provide a unified software where you can actually run these process-oriented diagnostics on climate and weather data. And we also want to sort of follow the mantra where we can help you write the analysis of the pod once and then run anywhere on whatever data. So that ties into some of the key points listed here in the bullets. If I want to help you run the analysis on different types of data, the MDTF framework has a bit of a backbone that relies on CMOR and CF variable naming conventions. But that doesn't mean we cannot handle the internal formats. There are capabilities in the MDTF framework, especially to facilitate model development, to detect internal GFDL formats, and also obviously handle the CMIP output formats, which are much more richer in terms of metadata and global attributes and such. There was also considerable improvement in testing in phase 2. Another thing I also want to point out here is that we started collaborating with DOE sort of informally in phase 2, which has now become an official funding mechanism. And we collaborate with DOE's CMEC, which is a coordinated metrics and evaluation capabilities, in coming up with these joint standards for setting and naming conventions, which are extremely important for developing standardized softwares for running analysis or metrics such as the pods. Next slide, please. So looking at phase 3 and beyond, I want you to focus on this triangle, mainly the 3 parts here. One is phase 3 will be focusing a bit more on, we'll be continuing to focus on the MDTF framework development, which we just talked about briefly. And then there's also another angle, which is the pod development. We'll continue to encourage more diagnostics to be incorporated into the framework from different modeling components. And these diagnostics span across different modeling components and also different like weather scales to climate scales. We're going to cover that in phase 3 as well. That will help characterizing variability. In terms of framework development, we also want to focus more on 2 main features, which is to allow multi-run capability, that is to help compare with different ensemble members or different perturbation experiments, for example, based on user feedback. It will also be great to have some provenance mechanism, like some sort of a storytelling from start to finish as you generate these diagnostics. Now, both the model, both the pod development and the MDTF framework development will then have to feed back into the model development, and that is going to help us build stronger connections between the task force and model developers at GFDL and NCAR. So this means the framework development teams will be closely integrating with the modeling center workflows itself for a seamless integration. This also means that we'll be focusing more on adding more diagnostics as well to help the community. Now, for all of this to be a happy ending, we, of course, from the framework development need to focus on usability, which means, how to make the installation experience actually better by using things like containerization. And how do we make the software more maintainable, because the framework is going to be running in more than one centers, and the maintainability aspect needs to be improved. So we'll be talking a little bit more about continuous integration, cloud-based continuous integration throughout. In terms of interoperability, something that I touched upon earlier, we want the framework to be working on different types of data sets for us to facilitate both model development and model evaluation. And we do encourage open discussions and collaborative code reviews. We will also have some sort of a contributorship recommendations or guidelines set up in the coming phase. Next slide, please. So this is a quick architecture diagram for the phase 3 framework, but there are just a few things I want you to focus on this. So the peach or the orangish boxes that you see are those that are coming from the contributed process-oriented diagnostics. So the pod tells the framework what the requirements are in the form of a configuration file, also called a settings file. And then most of the white boxes that you see are those that the framework is handling from the framework's end. It will do all the data ingestion, the data munging aspects, setting up the analysis environments and things like that for the pod to be able to run then. The framework again runs, the framework code runs, and then the plots are produced. Finally, it goes back to the MDTF framework, wherein the MDTF framework collects the output and just displays that in the form of a nice HTML web page, which you'll see in the next slide. So the purple boxes here in the figure are indicative of the newer features or the elements added in phase 3. Namely, can we work only with the local data sets? Can we also look into hooks where you can also interface with distributed data sets through data catalogs, for example? Can we also incorporate helper utilities, supporting utilities like feature trackers and regridding, so it becomes much more useful to the community? And thirdly, like I already mentioned, we'll continue to focus on the CMEC MDTF standards here. Next slide, please. So this is a quick example of how the output delivery is done from MDTF, just an example of the HTML web page from one example pod. The two takeaways from this slide is that it's very important for us to have documentation related to the pod from the pod developers, and we highly encourage that because it makes the pod even more usable. And of course, it also has links to plots coming out from the diagnostics. Next slide, please. So now I'll tell you briefly about the 3 C's that we may be focusing, phase 3 and really beyond that. Focus on the diagram to your right. So you see MDTF in a can, or imagine it's a container. So if you have run MDTF running in a container, that means there was some sort of a truth or a recipe for that in terms of specifying what went into installing your software and actually running it. So think of the container recipe as something that packages source code, the analysis environment, and all the dependencies. Now, having this container, you can take that and run it anywhere you want. So you can run it locally, or you can run it in your HPC facility, or if you want to talk about cloud, you can also deploy, or you can also run MDTF in the cloud. So that's a quick introduction to containers, which will help us simplify the installation and make it more portable, especially because we have multiple institutions involved. It also helps with repeatable software because we have everything described in that recipe that goes into creating your container images. So on the figure, again, if you want to focus on the cloud-based continuous integration, I already mentioned about the maintainability aspect. So we want to continuously focus on how to better our testing. Continuous integration simply means do everything often, review your code often, test your code often, and merge it often. And that's pretty much what continuous integration is to me. So we do have automated building and testing that's happening. Currently, we use the GitHub default resources. But as we have more set of pods coming into the framework, we are now already experimenting the use of cloud for scalable resources. Of course, beyond the CI aspects, we also want to focus more on having a production container image ready for the users to actually try it out. Since we are already working in the cloud, this also opens numerous other possibilities where you can leverage the use of community developed data cataloging APIs, and you can also use cloud optimized analysis workflows if your pod requires that as a backend. And we also now see a lot of public data being hosted in the cloud. So, we just have to aim for the sky and we'll start with the cloud. MDTF pods in the cloud could probably use existing publicly hosted cloud data, which means you will not be downloading data. You'll just be bringing your analysis closer to the data, which is going to be very interesting and effective in the future. Next slide, please. So this is a quick look at how the CI pipeline looks today. We do use GitHub Actions, and we also use GitHub hosted runners. The GitHub hosted runners, if you're not familiar with it, those are the servers that do the heavy lifting of running this workflow that comprises of the tests and the building and installation, for example. We do have code review set up with 2 or 3 people in the team having to review code for every push or every pull request that we actually have. In terms of testing, we do have unit testing modules and also testing that involves pods with synthetic model data generated by our homegrown package called the MDTF test data package. Other things in terms of the pipeline include we do have an LGTM software that has that does a little bit of checking in terms of the formatting and the linter and security analysis as well. Next slide, please. So going forward, we are experimenting a couple of different routes using the cloud itself. So we did talk about the GitHub hosted runners. So just replace that with something in the cloud, and that's the test that you're actually seeing here. So you have continuous integration pipeline using Amazon self-hosted elastic compute cloud runners, also known as EC2. So in this example, what you see is we just start a self-hosted EC2 runner in the cloud. So it's highly scalable, you can increase the number of cores, you can increase the number of instances up and down depending on the workload. And as soon as the job, in this case, a set of tests is complete, you can just stop the self-hosted EC2 runner, which means you're actually optimizing cost here. You just pay for what you actually use. The other things regarding the review and the exact test cases remain the same. Next slide, please. In the next test, we did employ the use of Docker images. As part of the pipeline itself, we built Docker images. So it was the automation was pretty much seamless in the cloud. We did make use of elastic containerization services, again from Amazon. They provide nice service stacks that are readily able to run these containers for you in the cloud. And we did not have to change our actual backend here or the workflow pipeline where it uses GitHub Actions for the container, for the continuous integration platforms. In terms of tests, we do plan to use AWS Codebill for application tests and to report the status of the test, whether it's a failure or success, hopefully success. So this is just to show you how there are so many services available in the cloud that help us drive these solutions at ease, spending a little less time on developing these tests in the cloud. Whether you have 2 pods, whether you have 20 pods, the framework or this testing framework or the CI framework can figure out the workload and play with your EC2 instances or the ECS dynamically. So it is, but in my experience, it's been highly usable and very convenient as well at the same time, without having to change too many things in the pipeline and keeping things simple as much as we can. Next slide, please. We also wanted to show that things can be done in different cloud service providers. So just to show the cloud neutrality, we do have another experiment that is led by our lead software developer using NOAA ParallelWorks to do a similar thing, but using Google Cloud. Next slide. I think I'll just summarize here the part one with take-home messages and let Wenhao lead the next section. So we just saw that MDTF promotes unified open frameworks for specifically process-oriented diagnostics. We love conventions if there is one, so see more CF conventions. And in terms of metrics and diagnostic standards, we are really looking forward to working with CMEC on this. And we are here to help the researchers actually focus more on the scientific research. So you write your script once and run it anywhere. We'll continue to strive for simplifying user experience. Those are the 3 C's that I talked about: the containerization, cloud, and continuous integration in terms of usability and maintainability. Add a D to that, and that becomes 3 C's plus D. D, we have excessive documentation on MDTF, and I encourage you to check it out. Hopefully, all of this fosters engagement with modeling centers such as NCAR and GFDL, and this should facilitate model evaluation and model development. Thank you very much. With that, Wenhao, please take over.
Sure, thanks, Aparna. So I will continue the talk by first introducing the MDTF framework as well as its application to the latest 3 GFDL models. And then I will talk a little bit about our recent work of the mesoscale convective system over US, sort of in-house developments of this package, which is actually inspired by this framework.
Wenhao, are you still there? I cannot hear you.
Yeah. Wenhao, your audio is gone.
I think I turned. How about now?
Yeah, I can hear you now.
So I start from this slide. Sorry about that. So as mentioned before, we have a bunch of paths that are available in this package. I'm not going to touch upon them all. Instead, I will choose to make use of the MGL paths to provide you sort of flavor of the so-called process level diagnostic. There are 4 of them analyzing different aspects of the MGO, including the phase, propagation, intensity, as well as its teleconnection impacts. I want to point out that all the plots shown in my slides are only parts of the results. There are more plots and information generated by the package that you can look at. So let's start with the wavelength frequency spectral plot. This is a very classical analysis proposed by Wiener and Kiladis in 1999 to demonstrate the equatorially trapped wave modes. Here, I just pick out the symmetric background power spectra to highlight the statistically significant spectral peaks. So the dominant signal based on the observation, the top left panel, are the Kelvin waves. I hope you can see my cursor. And equatorial Rossby waves, as well as MGO. And for the simulations, 2 things may attract our attention is that the large difference in Kelvin wave simulations, which show 2-week variance associated with these eastward wave modes. And another thing is the reasonable simulation of the MGO. Actually, this is great progress given that MGO remains poorly represented in most of the GCM, as well as weather model with non-nesting common pairs, including 2-week amplitude and the lack of systematic eastward propagation. So on base of this, let's take a look at more detailed features of the MGO. So here comes the MGO spectra and phasing module, the parts. It computes many of the MGO features by the specific MGO task force, including the lag cross correlations, UF analysis, composite life cycle of MGO. Here I only show you the results of MGO life cycle, that is the 8 phases during the cold months. So the shading here shows the OR alumni, where the vector shows the low-level horizontal winds. So you can see that compared to the observation, the AM4 model generally captures pattern, but the intensity as well as the eastward propagation are much weaker. While the CM4 and ESM4 model show better simulation in terms of the intensity as well as the eastward propagation, but we can see that the propagation and intensity of MGO are different in our three models, especially the AM4 model versus the other two. And based on these plots, we cannot tell what makes this difference. So the next part gives a detailed evaluation on the MGO propagation and its amplitudes. Here shows what you are looking at is the longitudes, time evolution of MGO over Indian Ocean and the Western Pacific. Compared to the observation, the AM4 model underestimates the eastward propagation scale in both regions, while CM4 model and ESM4 model give reasonable simulation. Similar situation can be found for the intensity, which is coded by the counter. So these results are consistent with the previous part, right? So we want to know what is the potential reason for these differences. So based on the moisture mode framework of MGO, the node-level moisture pattern on the right-hand side and the convective adjustment timescale of this moisture have been suggested to be important to simulate these features. So here we define the pattern correlation between these Hoover-Muller plots as the simulated propagation scale, while the pattern correlation between these moisture fields as the moisture pattern scale. When we put them in the scatter plots, it becomes very clear that we can see that MGO propagation scale is positively correlated with the moisture pattern scale with the correlation coefficient to be about 0.8 based on the model participating in the MGO task force. Similarly, we define the standard deviation of winter intraseasonal rainfall as the MGO amplitudes. And the convective time scale is defined as the ratio of the mean precipitation water anomaly to the mean precipitation anomaly over Indian Ocean. So it is a kind of measure of how rapidly precipitation must increase to remove the excess column water vapor. So based on these simulations, you can see that generally model with stronger MGO amplitudes corresponds to a shorter convective time scales. So this part provides a useful context for the correspondence between these metrics. A nice thing of this package is that when you apply it to your own model, say if you have a model being developed, it's easy for you to know where your model stands. So here's the result from the GFDL model. So you can see that they are generally in line with this correspondence, which gives us confidence to evaluate its interconnection impacts. As we know, when MGO convection propagates from the Indian Ocean across the maritime continents and into the Western Pacific, the response of the local circulation to the MGO convective heating anomaly could exert significant modulation on various atmospheric weather and climate phenomena like the ENSO, tropical cyclones, and extratropical weather system. So here comes our MGO interconnection part, which focuses on the North Pacific region. We choose two phases for the composite analysis to show you the interconnection patterns. So we choose phase 2 and phase 7. These two phases are characterized by out-of-phase precipitation anomalies over the Indian Ocean and the Western Pacific. So here's the composite results based on phase 2. Contour here shows the geopotential height anomaly, where the shading shows the tropical precipitation anomaly. The upper left is the observation panel with the 3 GFDL model and 6 semi-5 models which have been evaluated to have good MGO simulations. So you can find that though this model to some extent can simulate the basic feature of MGO, like its phase, propagation, intensity, their interconnection patterns vary largely. So similar results can be found in phase 7. So to better quantify the difference in the interconnection pattern between the model and the observation, the pattern correlations of the geopotential height anomalies between the observation and the model are calculated and averaged over all these 8 phases. And when we put them in the scatter plots against the MGO simulation scale measured by the eastward to westwards wavelength frequency propagation power, there is only a moderate correlation between these two elements. Then this implies that the ability to simulate a good mean state of MGO does not necessarily correspond to a good MGO teleconnection patterns. Then we may ask, what would be the other factors? As we know, MGO exerts teleconnection impacts while induced Rossby wave due to the convective heating. The direction and the propagation characteristics of these waves are actually determined by the background mean flow. So the relationship between the mean flow and the teleconnection pattern works a closed loop. Here in the middle panel shows the RMSE of the simulated upper level zonal winds against the MGO teleconnection pattern over the North Pacific region based on the 6 good MGO models. Only a weak correlation is loaded. This is not out of our expectation, right? Because we know that the Rossby wave usually travel along the mid-latitude jet stream. When we restrict the calculation of the RMSE over the core jet region, as shown in the red panel here, the correlation between these two elements increased largely. And overall, the model with larger MSE tend to have lower average teleconnection pattern scale among these good MGO models. But the robustness of this correspondence is queried due to the small sample size used here. In fact, the correlation has been undermined when we include the 3 GFDL models. You may point out that the CM4 model, shown as the green dots, is kind of an outlier where the other 2 models, the blue dots and red dots, are in line with these arguments, but we would like to have more analysis to explain these differences. So these 4 MGO modules compose the process-oriented diagnostic. I hope I've made this framework clear to you. So here is a quick summary. The package helps us to evaluate the MGO simulation by first looking at the simulated phase. We found that the coupled model is needed, indicating the RC interaction is important. Then it probes the propagation and intensity of MGO. We found that the low-level moisture pattern as well as the convective adjustment time of the moisture are important. At last, it explores the teleconnection pattern associated with the MGO. We found that in addition to a good simulation of mean feature of MGO, the background mean flow is also critical, and it also helps us to find out other factors may also play a role here. This would be an important topic since MGO teleconnection error may introduce uncertainty in future projections of extreme weather and climates that are significantly modulated by MGO. And this whole loop here helps us to pinpoint important guidance for model development toward an improved simulation of MGO. And next, I will use a couple of slides to talk about our recent work of the mesoscale convective system, MCS, over US. As I mentioned earlier, this is inspired by one of the pod, the Dyno Cycle precipitation. So here shows the summertime, Here shows the summertime Dyno Cycle precipitation over US. The hue indicates the phase of Dyno Cycle in local time, while the saturation indicates the amplitude of the Dyno Cycle. So all these 3 models, AM4, CM4, and ESM4, cannot capture the nocturnal peak of precipitation as of the observation. This is consistent with previous studies that the majority of the current climate model cannot properly simulate the Dyno Cycle precipitation. But we know that one of the dominant rainfall contributor over this region is mesoscale convective systems, which originate from the footfield of the Rocky Mountain and propagate eastward of the formation. So people are trying to argue that the coarse resolution in current climate model are not able to capture these systems. Some studies have shown that the bears could be reduced when the MCS are reproduced using the convective permitting model, but there are few works evaluating the climate model. While in GFDL, we have a higher resolution version of the AM flow model. So here is the oh, sorry. Here is the default version, which is about 100 kilometer, while we have a final resolution, which is about 50 kilometer. So you can see from by comparison, you can see the Dyno Cycle precipitation is a little bit better, but still not good enough in the higher resolution model. However, the final resolution model provides us a chance to examine the capability of this model is simulating the MCS. So here are the data and methods used in this work. The 3 hourly observed brightness temperature and the simulate OIR are used to identify and track the MCS based on these 2 widely used thresholds. Here are some details for your reference. The figures on the right-hand side shows the observed and simulated brightness temperature as well as their difference. As you can see, the model overall captured the pattern, the spatial distribution with a slight overestimation. This overestimation would translate to an underestimation of the simulated MCS, which I'll talk later if I got time. So these are the some preliminary results showing the occurrence and genesis frequency of MCS. Based on the observation, the MCS are generated at the east footfield of the Rocky Mountain, as you can see of the gray contours here. While they are shift eastwards in the model, and the frequency is better to know, especially over the Great Plains, you can see in the difference plots. We also examine the seasonality and the inter-area variability of both the occurrence and genesis frequency. Looks like the model is able to capture the peak in the warm season, but it fails to reproduce the annual evolution. Since we are using the 3-hour datasets, which enable us to take a look at the Dyno cycle, it is obvious from the first column that the observed MCS are generated near the Rocky Mountain in the late afternoon to midnight, as shown in this corner. That is when the nocturnal precipitation peaks over this Great Plain region. And based on panel A, we can even see a clear eastward propagation of the MCS. By contrast, they are mainly generated in the morning hours in the model. One nothing analyzed here is the MCS-related precipitation, the middle panels. On average, they contribute to about 40% of the total warm season precipitation, and the mean dry bears seen in this model could be partly attributed to the MCS-related precipitation. I think next we will try to understand what would be the reason of the model deficiency in simulating MCS. So addressing this question will definitely help us to have a better simulation of the precipitation, which itself will have important implications. So here comes our conclusion. Again, as highlighted by Aparna, the MDTF package is a powerful tool for model evaluation and model development. This package has been widely used across GFDL. In addition to the model analyzed here, it is also applied to the seasonal prediction model sphere, the implementation of a new microphysical scheme in CM4, the high resolution model development, etc. One thing I want to bring to your attention is there is an ongoing coordinated effort of the Atmosphere Model Task Force. The goal is to advance seamless atmospheric modeling at GFDL from the 2 major atmospheric modeling efforts, namely the shear weather scale and the AM4 climate focus. The current plan is to adopt the AM4 framework and introduce shear functionality to create a seamless system. And then we can use it to test and examine short-term forecast scale. And I think if that's it, I'll stop here for questions and comments. Thank you for your attention.
Okay, thank you very much, Wenhao. Thank you, Aparna. If you have any questions, you can reference the Google document. If anyone has any questions, you can reference the Google document. And I do see that we are getting some questions in. Aparna, do you see the questions? Wenhao, do you see the questions? Are you logged into the?
Yes, I do see one question coming in. Yeah.
Yes. Okay. And You can go ahead and address it if you are ready.
Sure, okay. I think I'll just read out the question, and I'm not sure if myself, Wenhao, or someone else from the MDTF team wants to talk about it. Let me just set for now. OSTI and WPO funded UFS R2O mega project is currently underway for the 3rd year, and a lot of prototype data sets are available for the community to analyze and diagnose issues to improve the models. What could be developed for the UFS community, focusing on the UFS R2O project? Thinking more on the applicability and ease of using the existing pods or developing new applications. Could you talk about the timeline for your CI/CD and adoption of pods? Is a CI/CD automatic? I think it's a sort of a 2-part question. Wenhao, would you like to address the first question? And also, Stacy, from my end, I am able to unmute David Nealon. If that's okay, I can do that since I think it'd be great to get his input too.
Yeah, sure. If you're able to unmute whomever you would like to address anything, absolutely. Please feel free.
Okay, sounds good. So, Wenhao, do you want to take a first crack at it, or can I unmute David or E or anyone else that's wanting to chime in?
I'm still looking at this question. Probably you can unmute E or David if they have any ideas.
David, you should be able to.
This is David Nealon. Can you hear me okay?
Yes.
Yes.
So this is these are great questions. One of the things I would say is that, this, the intent of doing this presentation here is partly to let you know what we are up to so that we can get input on things that would be good to coordinate with. We do, as everyone does, have to be careful to balance the things that we are specifically funded to do with connectivity to other things, but these, there's very often connections that can be made that are extremely helpful. So getting the input and also seeing who the people are that it would be best to discuss this with could be extremely useful. I don't see who was the question asker here. It was Anonymous Python. It would be useful to have that name in there if we can do follow-up. In terms of timeline, probably Aparna, you would be the best one to answer for the CI/CD. For the pods, the pod development is funded for various small research groups to develop over a 3-year period. So we have currently coming in the pods from the last phase, and we have another 9 or so groups that are funded to bring in more process-oriented diagnostics over the next 3 years. And we can, for instance, the example of CMEC was a case where we could spot an opportunity to create common standards and tools for not very much extra overhead that would allow us to collaborate on climate analysis with respect to process-oriented diagnostics and metrics respectively. The weather direction is one that we haven't specifically opened up in the sense of forecast. So we're not set up currently to handle forecast mode runs, but being able to discuss that with people from UFS R2O would be great.
Oh, yeah, great. Thank you so much, David. Regarding the timeline for CI/CD, one of our cloud grants, I think we need to deliver something in a year's time. This is especially with a cloud-based continuous integration. But in terms of the GitHub hosted runners that I talked to you about, that's already operational. The CI part is automated. I won't say it's fully automated because we do require some sort of a manual review in the process. So that's the only part that cannot be automated because we definitely need people to actually review the code. But otherwise, I think everything else is automated. Yeah. Does that help? Any other follow-up questions with that? Okay. All right, I do see another question. Why would you open up to weather verification when there is MetPlus available for that?
And Aparna, were you going to take that, or should I jump in?
Yeah, feel free to jump in.
I'm not sure I completely understand the question. The Model Diagnostics Task Force is neither looking to, nor would there be the person power available to compete with MetPlus. I think this may have been in response to my comments about being open to dialogue with the things that were identified in the previous question. There are often things that can be beneficial to two communities. So I hope that answers the question. I'm not sure if I have understood it correctly.
Stacy, I don't see any other questions here in the doc yet.
Yes, I don't see any other questions either. So that was the last question. Okay, thank you all very much. We're just gonna wait a little while to see if anyone else wants to add anything. But in the meantime, I wanted to let everyone know that if anyone has any recommendations for speakers for the future, again, please email us at ufs.modeling@noaa.gov, and we will be able to respond to your recommendations. And we're also going to have a poll out for anyone who wants to recommend any of the speakers. So, and yeah, there aren't any other questions.
Stacy, this is Krishna. Yeah, I basically asked the first question and the anonymity is gone now. The OSTI, I mean, David was asking about who the point of contacts are. We have actually Vijay Tallapragada and Jeff with Jeff Whitaker are the two POCs from, OAR and NWS. Maybe I think my premise was more on the applicability of, these pods and any of the new, and if somebody wants to develop something new, how easily could that be adopted for these kind of applications for research projects, And also I have a related question on the weather timeline, that MetPlus and weather verification, because there is the pods available for MCS. Are there any kind of collaboration with SPC and other centers?
No,
Okay.
currently we don't have, because we just try to evaluate the model. So what I have shown today is just preliminary results. We don't, because in the literature there's no many studies, examine the climate model, and we're trying to see if the high resolution model using GFDL could capture the MCS or not. And maybe later probably we will try to take a look at other modeling centers or other observation studies looking at this.
Okay. No, are there any other questions? I think to make it easier, if anyone has any questions, they can also raise their hand just for clarity. And I do see one hand raised. Is that Yi Ming? Aparna, I don't have the capability to unmute. If you would like to unmute that hand that you see raised, if you see it in attendees.
Yep. Yes. Go ahead.
Yeah, I was just unmuted. So there are a few threads here. I think I'll start by addressing the MET, the MatPlots tool. I think a major difference here, especially from the MDTF package, is that for MDTF, we're looking for process level diagnostics. So in that sense, we want to know whether you're getting the right answer for the right reasons. So it's not merely a sort of a forecast validation tool. Actually, we do have a sort of pending proposal that is to build MDTF-based pods into MatPlots so that UFS community can just use the existing infrastructure associated with MatPlots to run MDTF pods. So that's certainly a part of our outreach effort to UFS community. People also mentioned that there are existing experimental simulations on the UFS side. David made a very, very valid point. Right now, we're not funded to for that kind of application. There are also technical issues associated with dealing with short forecast runs. We're trying to address them. But as far as I can see, especially within NOAA, there is no sort of showstopper that would prevent us from at least doing some sort of proof of concept to apply existing pods to existing UFS simulations. So if we can use that as a way to sort of better understand each other's needs and the requirement along the way to build up mutual trust, I think that will be a highly worthwhile investment. So if there is anyone willingness to be on the sort of receiving end from the UFS side, who wants to sort of give MDTF some sort of a tutorial how to run those things, how to access the existing simulations, just please feel free to get in touch with me or David or anyone on the MDTF team. We can see what we can arrange. Thanks.
Okay, thank you. Aparna, is there anything that you'd like to add? We are going to close out now.
No, I don't have anything to add. I just want to say thank you to all of you for showing up here today. And thanks, Wenhao, for presenting along with me.
Yeah, sure.
Absolutely. Thank you very much, Wenhao. Thank you, Krishna, and thank you, Aparna, for even attending and your presentations. Really appreciate it. And again, we will be reconvening next year. So you all have a wonderful holiday. The next time we are going to present will be January the 12th, okay? Thursday, January the 13th, 2022. You all have a wonderful rest of the evening, and thanks again for joining the UFS webinar series.
Thank you, Stacy.
All right.
Thank you.